Hello, my name is Kevin Kwan, and this is Physics Lab 1 Constant Velocity. So introduction, the purpose of the lab is to model and analyze an object moving at a constant velocity using experimental observation and computational modeling. For the lab, the materials used are tape for the object, tracker for calculating the observed displacement, close grip for calculating the expected displacement, and ruler for calibration. The model was rolling an object across the table and analyzing its motion. The fundamental physics principle applied here is Newton's second law, which states that the rate of change in momentum is equal to the vectorial sum of forces on a body. The formula for Newton's second law is that F net is equal to delta p over delta t. From Newton's second law, we can derive the velocity of the formula by multiplying delta t to both sides of the equation and changing the delta p to uh, momentum final minus momentum initial and adding initial to the both sides of equation and dividing the entire equation by mass on each side. So overview, the system is includes the tape and the gravity, and the surroundings include any other force acting on the tape, which includes friction and air resistance. And overall, the expected motion predicted a slightly greater displacement than the actual recorded motion. So this is the tracker observation video where the tape was rolled starting at 0 seconds all the way up to 1 second. As you can see in the graph, the slope of the graph is positive for displacement because the ball is going at a constant positive velocity every second. So using tracker to calculate initial position and velocity, the initial position given is 0.007443 meters, and for initial velocity calculation is velocity initial plus velocity final over delta t, and I use the first zero point 0.1 seconds to minimize error, and that gives us 0.32893 meters per second. For the computational model, first, I switched the ball's position and ball's initial velocity on lines 35 and 36, and I changed line 40 delta t to 1 over 60 because the video was 60 frames per second. And on the actual graphing, I changed the while loop to t is less than 1.0 because the motion was for 1 second, and I updated the ball's velocity formula using the velocity update formula found earlier and ball's position update formula by multiplying by delta t on both sides of the equation from the velocity equation. So this is a graph of the observed motion versus the expected motion. The expected motion is from the glow script where the motion is considered frictionless and everything else is perfect. And the observed motion is the actual motion observed from tracker, and that gives a slightly lower displacement because there are other forces acting on it, and in expected motion, everything is perfect. So possible sources of error include friction on table, air resistance, and human errors when plotting on tracker. Friction and air resistance will both exert opposite force than the motion of the object, which decreases the overall velocity. And as you can see on the picture, the plotting is not consistent as it is done by human. What if the axes were flipped when observing motion? The net force on it would still be zero, but the initial velocity would be negative. And if the initial velocity is negative, that would cause the displacement to be in the negative direction. So conclusion. In the computational model, the model assumes the surface is frictionless. That means if the net force is zero, the only forces acting on the ball while the ball is moving would be force of gravity and normal force, which cancels each other out. In the real world, however, the model includes friction and air resistance. Even though the force of gravity and the normal force cancel each other out, the forces in the x direction are affected, which causes the ball to slow down and have external force exerted on it.